Thank you, and thank you to all the organizers for the opportunity to present some of my recent work here today. So, I mean, it's actually great. I'm really happy to be here because I've been on the plateau for just about a year. So it's good to meet another institute and some new people. So, right. So I'll be talking about the investment banking key distribution. So here's the outline of my talk. So first I'll just present some of the context, then mention some of the steps of the protocol. We'll see if we have time to go into the security proof or not. And then I'll mention an experiment that was done in collaboration with Oxford. And there were shortly after 2 other experiments that came out. And those are the references in case you're interested. Okay.
Sorry, I have to speak.
Okay. Just remind me.
Ok, je ferai ça de temps
Oh, pas de problem. All right, so let's get started. And so to set the context, I'll proceed backwards from the title. So let's start with key distribution and what is this about? And well, this is actually a cryptographic task. So let's see what cryptography is about. And so a typical cryptographic scenario is one where we have parties or users. So here we have 2 parties, one called Alice, one called Bob. And those are distant and they could share some information. Maybe here, they share a variable key K, which will be just a bit string for the sake of this context here. And they could have also some information that is not shared, say here the variable M. And we can just ask generic questions, for instance, how could Alice send this variable to Bob? So obviously one way to do that is just by using a classical channel and actually sending the message. But there are other ways to do it. And one interesting way is the so-called one-time pad, which consists in basically computing the XOR of the message together with another variable, the variable K, and transmitting, instead of M, transmitting the variable S, the result. And when doing so, Bob will be able to actually extract or decode the variable M by computing the XOR as well. And you'll say, okay, well, that's just a complicated way of doing something simple. But this has some very interesting properties, because if you think in terms of entropies, well, this scheme has the property of having basically no uncertainty about the variable M for people having access to both S and K. This is why Bob can decode the message. But at the same time, there's absolutely full uncertainty about the message for anyone having only access to S. So, and what this means is that now in this setting where we have separate users.
Sorry, the 2 words M and K have the same length.
Yes, yes. Yeah, in this case, yes. Yeah, you want to have them match, yeah. Mm-hmm. Exactly. So you have a length n bits, yeah. And so, yes, the advantage is here that, well, now if Alice has maybe her space or her lab, and she has access to it, but she doesn't really control what is out there, and Bob similarly, well, if they use a public channel, then this information going on the channel could be accessible to other people. And so this, we want to make sure that, okay, this S does not carry the information on the initial message. That's what cryptography is about, right? And so what we see is that, well, this, yes?
What's the definition of H and S?
Oh, this is the entropy, so the fundamental entropy or Shannon entropy. It's a conditional entropy. So it's like if you want, it's the randomness or the uncertainty you have on the variable given access to S or to both S and K.
You assume that M is taken at random?
So yes, here it will be like for a string m taken at random. Yes, you're right. All right. So, and of course, this works provided that also k is secret or is a key, or that means in particular it's also taken at random, so it's unknown to whoever is the adversary here. So, well, this is what happens in cryptography, is that we see that secret keys are actually a useful resource for various protocols. So a natural question is, okay, well, how can we now create such a key in order to do something like that, or even other protocols that are possible with such keys? So we could imagine now another protocol, which would be, again, involving our users, where they will start communicating and doing some maybe local computations and ending up with some key, KA for Alice and KB for Bob. And ideally, we would like this protocol of generating the key to produce identical keys. And we'd like nobody else in the middle to be able to have the same key, right? And as it turns out, such a protocol does not exist. And it's very easy to see why, because if a protocol like this existed, then whatever Bob was doing in the protocol, the adversary could do the same to Alice. And whatever Alice was doing in the protocol, the adversary could do the same to Bob. And then the protocol would just create a key between Alice and the adversary, another between the adversary and Bob. And therefore, the adversary would actually have a copy of the key. Therefore, the key would not be secret. Okay, so this is a very standard attack, which is called the man-in-the-middle attack. And this is basically why all of public communication requires authentication. And the way to authenticate is to actually start from an initial secret key. That could be small, but it needs to be there present in a way. Right? And then, then somehow to rephrase what we want to do here is maybe we don't want to create a key, but maybe we want to, starting from an initial small key, we want to expand it to create another one that will be longer or much longer, ideally. Okay.
So this initial key, K0, is shared by Alice and Bob, right?
Exactly. This will be, in a way, this will be the way that they can identify that they are talking to the right person, because otherwise anyone can impersonate them. And there's no way. It's like when you meet someone that you have never seen before, how can you know that you're talking to the right person if you don't have something in common, some information? So that's basically the same problem here. So, okay, maybe you're wondering, okay, but how, wait, we do communication, secure communication on the internet, connecting to our bank and so on daily, and we don't have to ask these kind of questions, right? So what happens? And of course, the answer is that, well, what is done today relies on some computational assumptions. So what this means is that essentially those are mostly, they rely on one-way functions. So those are basically functions that are easy to compute, but who are believed to be hard to invert. So one example is factoring numbers, right? It's easy to take the product of two numbers, but to find the initial factors, this is believed to be a hard problem. And therefore, this is what is used today to create security in communication. But as you maybe know, this kind of assumptions is kind of problematic, because as we know, in the case of factoring, and also in the case of even elliptic curves and other, if you have heard those terms, well, those are all tasks which are difficult for classical computer, at least believed to be classical. We don't have a counterexample, but we know actually that they are easy for a quantum computer. And so a quantum device could potentially break those.
Sorry,
Yes?
I'm a bit confused by your argument. There is
Okay, so I'm a bit confused by something you said in the past. You say that there is no classical protocol to share a random private key, but I thought that there was the Diffie-Hellman protocol, which can do that. So I was wondering where.
So it's using this.
It's using
one-way functions.
One-way functions. Okay.
So it's basically, and that's what is used. I mean, everywhere. Mm-hmm. But it basically relies on functions that are believed to be hard to invert.
Okay, I see. Thank you.
And the way that basically the way that the day that you can actually invert those functions, then you can break all of those communications. But you're right. Yes. All right. So, and this is where basically quantum theory comes handy, because if we take even a simple 2-qubit system, which is maximally entangled, psi minus, then we know that the results of measuring this state locally will create outcomes which are fully unpredictable by basically anyone in the universe, according to the theory. Okay, this is because, well, the singlet state is pure state. It cannot be even correlated to any other system. So we see that, well, basically by measuring a singlet state, in a way, what we're creating is creating something that is truly random. And by measuring at a distance, we can also actually obtain fully correlated or anti-correlated results. And this basically are the properties of a random private key, right? So, well, why not use that? And indeed, this is possible. And we will still have to rely on some assumptions. And so those are the assumptions that are needed here. Well, we need to trust quantum theory. We need also, that's a fundamental assumption, but we also need very practical assumptions. So for instance, as before, we are in a cryptographic setting. So we say that Alice has a lab and she can control what is in the lab. So this means in particular that she can control what information goes out of the lab, because otherwise there's no point in doing cryptography if everything that Alice is doing is available to everyone. So that's an assumption. Then also the measurements, the choice of measurements that are done on the system must be correlated to the system themselves.
Sorry, can you?
Yes?
I didn't hear.
Oh,
I just didn't hear what
sorry,
you
I
said.
don't know. So I just said, so the third assumption is basically that the choice of measurements that are performed on the system must be independent of the state of the system itself. It's more technical assumption, but it's an assumption. And also, it's maybe more technical, but somehow we'll have to do processing, and this processing must go according to what we expect. Because if we are a protocol doing something random and at this end saying, yes, your key is secure, well, that will not be helpful, right? And actually, similarly here for the quantum devices, so when we say we measure a single state, actually, if we measure a different state, then maybe the security will be corrupted, right? So this is also an assumption. But as you can see, there's no assumption here about the computational power of the adversary. And so this is where we get something really different than what is was known before. And in this sense, the security is information theoretic. Right. So, well, quantum key distribution protocol based on these intuitions have been known for a long time now, and you can even, they are even implemented. You can even buy a system that will perform this for you. And people have come up actually with also attacks on them. So we could ask, okay, why? I thought this was like secure. How can you have an attack on such systems? And basically the reason behind those attacks are that in practice, the states are not exactly the state that was supposed to be. And also the measurements might not operate exactly as we want them to be. And if you think about it, say this would be maybe a photon detector, a single photon detector. Of course, it's a device which will detect photons with some efficiency, but this is only, in reality, it's actually a complex system which contains a lot of physics. And so it will only behave as a single photon counter when operating in a regime. But if you are able somehow to bring this apparatus to perform in a different regime, it will actually do something very different. And this is what those attacks are basically doing, is making the devices operate differently than what they were aimed to be doing. So, okay, we can ask, well, how do we avoid this, so there are several ways. One way is just to say, okay, every time we find an issue, an attack, we can add a countermeasure to that attack and hope that as time goes, we get something that is more and more secure. That's one possibility. Another possibility is to say, okay, well, instead of adjusting the implementation, let's change the theoretical analysis and just really put the full model of the setup, the full model of the detector into the theoretical analysis and try to prove security there. But this also is very impractical because first, we don't have a full model of everything. And even then, it would be just extremely cumbersome to get any concrete proof out of there. So what we're pursuing is a third option, which is to say, okay, instead of adding more details in the description, let's remove details from the description and try to basically get a description of the setup that is so sparse that we can hope to have a match with the actual implementation. And so this is what device-independent quantum key distribution is about. And what it looks like is basically saying, well, we have a source, but we'll just say that the source is a box that creates something. And when it creates something, maybe we have a signal that tells us, okay, something was created, and we don't know what it is. Similarly, for the measurement, we'll have a box where we can make some choice between one measurement and another, which will just be a button we can press. And every time we press a button, we get also a discrete result. And we'll say, okay, that's just the way we describe our system. And we don't want to say exactly how this outcome is produced, right? And when we do that, basically we are working under the same assumptions as before, except that we are getting rid of this last problematic assumption. So we could ask, okay, well, but we could even remove more assumptions, and get even more general. That would be, but maybe at some point we just cannot get a result anymore. So can we actually do anything in this regime? And the intuition here is was brought already by Madison Yao in 2004, is that, well, even if we don't assume the state being produced being something specific, like a single state, maybe the statistics that we observe will allow us to infer that this is the state we measure. And if we are able to infer it, then we should also have the property of the usual QKD protocol. So how do we do that? Well, the way to do it is to basically play a non-local game, such as this CHSH game, because it has the property of distinguishing between classical and quantum strategies. And in particular, we know that, so this is a game that can be won up to 85% of the time with quantum theory. And it has the property that actually there's only one state that can bring you this winning probability, and it is the single state. So in this way, you can actually identify or certify the state that is being used. So things should work, right? That's the intuition. And to be more precise, already in 2009, Stefano Pierogno and other co-workers, they actually estimated what was the uncertainty about Alice, that an adversary will have on Alice outcomes in this black box scenario as a function of the winning probability. And they could verify. Sorry?
With Ed.
Okay, sorry, it's the adversary.
Oh, sorry.
Yes, I didn't introduce her. That's sometimes we call her F. Yeah. And so, as you can see, with the winning probability going up to 85%, the uncertainty of the adversary is going up, meaning that she knows little and little. All right, so thank you. All right, so let me just give you a brief overview of how those things can be put together to actually reach a protocol producing a key. And so basically in the protocol, there will be two main steps. One is the quantum part, where we measure quantum systems, and the other is more about actually processing this data we obtain. And so, well, the quantum part is will be essentially to generate a state. When the state is generated, isolate the labs, make sure that no information can come out from there, and perform a measurement. And this has to be just repeated a number of times to generate the raw data. And in practice, there will be like two kind of rounds here. One will be test rounds, and the idea is to try to play this non-local game during those rounds. And during the generation rounds, the idea would be to actually try to make the post-processing that will come afterwards easier. And importantly, there is one choice of measurement here, x I equals 0, which will be identical between two in such a way that the adversary is not able to know whether we play one round or the other. And then once the data is produced, that means Alice will have a string of outcomes, Bob has a string of outcomes. Well, they need to process that. And the very first step, it will be to check what is the winning probability that they observe during the protocol. But for this, they need to compare the outcomes. And they cannot just reveal the outcomes because then it will be available to the adversary. So somehow, Alice needs to reveal her outcome to Bob in a way that is not, well, needs to reveal enough information about her outcomes that allows Bob to recover them without also giving too much information to the adversary. So that's the task of error correction. And so it has to be done carefully. And then after that, well, Bob will have all the information. He can check that the non-local game was won significantly. If this succeeds, then they can proceed to privacy amplification, meaning extract the actual randomness from the string, because the string will not be fully random, so they will extract just the random part. And in the end, they need still to authenticate their communication to make sure that there's no man-in-the-middle attack, that they were indeed doing all of this with each other and not with a third party. And each of these steps, of course, can either pass or fail, and we are only interested when all of them will succeed. So maybe just very briefly, so the security, then the final security of the protocol will actually have several components, and those are basically, we want the keys to be identical, so we call that correctness, and we also want the key to be unknown to the adversary, we call that secrecy, and this can be just parameterized by a single parameter, we call the soundness. And so the soundness depends on the correctness and secrecy, and in practice, we'll have some hash functions that will play a role here, and we'll have the extractor as well. And finally, what really needs to be computed is actually the parameters that will need to feed there. And in particular, we need to give here a bound to the extractor of how much randomness there is in the that we can certify in the outcomes. So maybe I won't go into too much detail about how we do that, but the idea is to, I mean, the key element is this relation that we saw before that relate the entropy to the winning probability, except that that one was kind of computing in an ideal case where we just know exactly the winning probability, and we need to adapt it to a sequential scenario in which maybe the system could change from round to round and so on. So this basically requires us to use something called the entropy accumulation theorem. And this then allows us to really get a bound on the entropy that depends on this curve with a minor correction factor of the order of square root n. So with this, let me just give you an overview also of the experimental setup that was used at Oxford. So this is a trapped ion experiment. And so they have two distinct traps, each of them with their own electronics and computer attached to it. And each of their trap has a possibility to move ions actually around. And what this allows them to do is actually prepare a state and then move it in front of a lens that is coupled to a fiber in such a way that the atom can emit a photon on both sides, and they can perform Bell state measurement here, which will be doing entanglement swapping and actually entangling the two ions that remain in the traps. Once this is done, this is like the state preparation, if you want. Then they can actually move the ions away from the focus of the beam to isolate their labs. And they do that on both sides. And then they can perform a choice of measurement, measure the ions, record the result, and start again. That's how things work. And their setup is good enough that they get a winning probability of about 0.83, which is really high. And also a noise when that can go as low as 1.5%, which are really extremely good numbers. And this over more than 1 million successive rounds. So knowing that, we took parameters, took the following parameters. Basically, we were a bit conservative to make sure the experiment would succeed, and chose the soundness parameter of 10 to minus 10. To say that. And okay, I'll just pass on that. But those are the actual protocols that we chose. I mean, maybe just one point about here is that, okay, of course, if we want to have information theoretic security in the end, it's not sufficient, of course, to just do things with a quantum system. All the components, even the classical components that come into play, they must also be compatible with that, obviously, right? So this required actually a careful choice of those primitives, which are not always the ones being used in the standard, I mean, in our computers, say. And with this, okay, this is the full protocol, and working with 1.5 million rounds and sacrificing basically 300 of those rounds for error correction, we're still able to generate a key of length 95,000 with an initial key of length 256. So we see that there's really an expansion here going on. And so this was work performed with all of these people, which is a collaboration between Paris, Oxford, Zurich, Lausanne, and Geneva. And so with this, thank you for your attention.
Thank you. So do we have questions?
Yes, thank you for the talk. Just a curiosity on the final part. How far is this from being really used in, let's say, real life technological, technical applications?
I mean, this is like the very first time this can be done. So obviously the setup they have is handmade, you know, it's like, I don't know how many years they put into it. But well, I guess it would take years, you know, to make it more just standard. But I think there are a number of groups actually working on that, and I guess there's no surprise. We kind of know the way to get there.
Okay, so there is, I mean, it's reasonable to expect that we will get to practical applications of this, or so are there big obstacles to solve, let's say, or it's just a matter of time and money and people working on it?
Yeah, I think it's mostly now somehow we know it works. And so, yes, just a lot of effort I mean, even somehow here we use one setup, which was just very good. But if you want to make it practical, maybe you need to use maybe a photonic setup would be more appropriate for a real experiment, for real life, you know, or something else. So this obviously is a lot of work. I think it's like, we know kind of where this could go, but the work needs to be done, yes.
Thank you.
Okay, other questions? Submit.
To understand the security, so at the end you generate a key. So I understand that Eve doesn't have access to it, but is it sure that even a few bits are not known to Eve? Could it be that maybe out of your 10,000 bits in the key, maybe a few of them could be captured anyway? Is it excluded?
So yeah, so that's a good question. So the notion of security here is really is actually captured by this condition here. So we chose epsilon sound to be 10 to the minus 10. So this one has to be also smaller than 10 to the minus 10. So it's very low. And what it means is, and this is really measuring the distance between the actual state of the key, the actual key and Eve's system, and a fully random system for Alice and the system of Eve. So this means that really it's like in terms of distance, these two strings are really close to 10 to the minus 10. So not even one bit can be known. And
thank you.
Yeah.
Okay, this was a bit my question also. So with this kind of experimental protocol that you show at the end, you are 100% certain there will be no external intrusion, or there is still a small chance that things go wrong?
No, I mean, so let me just come back to, yes. Those are the remaining assumptions, right? So of course, I mean, what we do is we have a theorem, and the theorem relies on assumptions, right? So as long as you satisfy the assumption, then you have the security.
100%.
100%. But you can, okay, maybe the first one, if someone has an idea to break this one, I'd be interested to talk to him. But it's actually possible to break some of the other one in a practical implementation. One way to break the second one, for instance, is just to go with a USB stick into Alice's lab and plug it in, you know? And so in practice, in a real world setting, I mean, there will be, of course, attacks that are possible, but essentially, you have to break something that is different than what was available before.
Okay, thank you very much.